A random matrix is a matrix in which all the entries are chosen randomly. So let's A be a matrix whose entries are Aij, where Ij varies from 1 to n, and these Aij's are chosen randomly. Random matrices were introduced in statistics by a statistician named Wishart in the year 1928, where he introduced fixed n by n random matrices, and he studied correlations between different statistical quantities. But more interesting properties of random matrices arises when n goes from finite to infinity. But today we will look at one property of an n by n random matrix, and in particular we will ask this question. Given a random matrix A, what is the probability, what is P, that A is full rank, or rank of A is n? The short answer, 1. So here we are not considering any corner cases, as theoretically we will get the answer to be 1. And what are we saying here? So we are saying here, if we generate a set of random matrices, let's say an n by n random matrices in let's say thousands of numbers, each time we will get a matrix that is full rank, or the columns and rows of those matrices will be linearly independent. We will give a intuitive proof of this property. We will not give a mathematical proof, but we will first look into some linear algebra basics, try to remember what a rank of a matrix is, then we will solve a probability problem, and we will try to apply the same ideas to solve this problem. So let's do some linear algebra basics. If you guys are familiar with linear algebra and probability, you can skip this part and directly go to the end of the video and just watch the solution. So in every linear algebra course, the subject starts using linear equations and solving linear equations. So let's take two linear equations. 2x plus y equals 0 and x minus 3y minus 3. Let's plot these lines. So this has one point as 0, 0, and one is when x is 1, y is minus 2. So let's draw a line that passes through 1 minus 2. This may not pass through 1 minus 2. Let's assume this will pass through 1 minus 2 and 0, 0. And this one, if y is 1, if y is 0, x is minus 3. If x is 0, y is 1. Right? Okay. So this is our solution. Let's name our solution minus a, b. So we plotted the lines of these equations. Wherever the line meet, we will get the solution of this set of linear equations. If you are doing it in a class, what we do is that We'll substitute the value of y in the second equation in terms of x from the first equation, then we'll find x, then we'll resubstitute the value of x and then find y, right? In linear algebra, we'll look at this from a different perspective. So we first write this equations in terms of matrices. So there is 2, 1 and 1 minus 3, and the other one is x, y is equal to 0, minus 3. We can rewrite this in this manner: 2, 1 times x plus 1 minus 3 times y is 0, minus 3. So here let's draw this vector space picture. This is a 2D vector space. First component is 2, 1, 2, 1. It will look something like this. And the second one is 1 minus 3, something like this, and 0 minus 3 will look something like this. And here the problem has changed. Here we have two vectors, 2, 1 and 1 minus 3, the column vectors, and we are asking the values of x and y, which are the coefficients for linearly combining these two vectors that would fetch us the output vector 0, minus 3. So let's say this vector is u, this vector is v, this vector is w, this is u, this is v, this is w. How do we solve this equation? We call this a, we call this x, and if we call this q, then x is given by a inverse q. And if we solve the equation, we'll get something like this, right? We'll get here, so this will be minus a, this will be b, so w can be achieved by linearly combining u and v in this manner. Here the solution is minus a, b. So the linear algebra transforms the problem to a linear combination problem, and we are asking that given two vectors, what are the coefficients we can use to find the third vector, which is 0, minus 3 here. So what we have done here is that using u and v, we have constructed a vector w, or find the coefficients for constructing a vector w in terms of u and v. If we can construct any vector in the vector space using u and v, this implies u and v are linearly independent. Also, we call the span of, then we say span of u and v is the vector space, which is a 2D vector space here. And if we place u and v in a 2 cross 2 matrix A, then the rank of A will be 2. But what if U and V were linearly dependent? If U and V were linearly dependent, then it may look something like this. This is our vector space, this is our U, and this is our V. This is V vector, this is U vector, and any linear combination of these two vectors will fetch us a vector along the same direction. In this case, we can also say the U vector is same as V vector. So this can be expressed as U is some scalar times V. So if we place these two vectors in a matrix A, then rank of A will be less than true. So I think the idea of rank is clear right now. So let's do a probability problem. Probability problem. So let's say there is a rectangular floor. We are standing in a top floor and we are looking at it, and there is a circular design on the floor. Now we would like to drop a ball from the top. We are dropping a ball from the top. I should have used a different color, right? Okay, let's use red or yellow. Then we would like to know what is the probability. What is the probability? What is P that the ball falls inside the circle. So what is the probability that the ball hits the circle? In this case, we know the probability will be area of the circle upon area of the rectangular floor. So in this case, this need not be a circle, it can be of any shape. In that case, what we need to do is we have to integrate. So let's say this is some other shape. We have to integrate the area, this region, find the area of this region, then integrate the entire floor area, and this region, area of this region upon the entire floor area will give us probability of the ball hitting this region when we drop a ball from top. And we have assumed that the probability of the ball hitting any part of the floor is equally likely. We can extend this idea to higher dimensions as well. In case of a circle, this can be a sphere, and in case of a rectangle, this can be a cuboid. And in 3 dimension, we can ask what is the probability that a randomly chosen point within that cuboid will come from the sphere. In that case, we can say that the probability would be the volume of the sphere upon volume of the cuboid. So we will use this idea to solve our problem. So let's try to solve our problem. Let's go back to our vector space. Let's take a 2D vector space, and and say we have two vectors in the first quadrant. Let's say we have sampled these two vectors and we would like to know what's the probability that these two vectors come from the first quadrant. Using the area idea, we know the area of the first quadrant is 1/4 the area of the entire 2D space, so the probability would be 1/4. If it was in 3D, we have octants, 8 of them, so the probability of two vectors sampled, two three-dimensional vectors sampled from 3D space coming from one of the octants would be 1/8. Right? Now let's ask a different question. Let's go back to the 2D space, but let's ask a different question. What if we sample two vectors and that vector come from a line? That vectors are collinear or that vectors are a scalar multiple of each other. So we can apply the same criteria here. So this would be, the probability would be area of the line upon area of 2D space, which will be 0 because a line has no area, it has only length. In the same way, we can ask in a higher dimension, let's say in 3 dimension, we can ask, let's draw it here, in 3 dimension, we can ask what is the probability that three three-dimensional vectors drawn from this space come from a 2D plane. All these vectors are lying here, this 2D plane. This will be, we'll write it here, P will be volume of plane by volume of the 3D space, which is again 0 because a plane has no volume. We can extend this to n dimensions. In n dimensions, if we sample n vectors sampled, then we can ask what is the probability that these vectors lie in n-1 dimensional subspace. Lie in. So this is the same idea that we discussed before. The answer would be 0 because n-1 dimensional entity has no volume in the n-dimensional space. So if we sample n vectors, then we place it in a vector, in a matrix A, which is n by n. Then each of these vectors will be linearly independent, which implies rank of A would be n. So we have proved our initial problem. So let's verify our theory using this code. Here we generate a random matrix for 1000 iterations. The random matrix is of size 100 cross 100 and it is generated in the interval 0 to 1, sampled uniformly. We compute the rank each time and append that to a list. Finally, we will print out the list. According to our theory, we should have the output as thousands of hundreds. 1000 hundreds, right? because we are expecting the matrix to be full rank each time we sample. So let's verify that. So here we have the verification. Each time the matrix is found to be full rank.